Sebastian?
Because you still can, it's still an indeterminate.
So, no, I mean, there's I think more value in the first person, but it also doesn't care how. So long as I'm there, I can still use this. Good question. Anybody else? All right, I think that was where we left off. Okay. Natural log of x over the cube root of x. Want to find that limit as x goes to infinity. Are we allowed to use L'Hopital's rule? How come? Not infinity. Well, infinity over 0 is not a time we're allowed to use that the L'Hopital's rule. So, do we have infinity over 0? You have infinity over infinity. Yeah, the natural log increases. You know the word monotonically means that as x increases, the natural log of x is always increasing. That same is true for the cube root of x. So they both increase monotonically with no upper bound. They're just going to they can get as large as you want them to get. So because of that, we have an indeterminate form again. So I can instead look at this limit, the limit as x approaches infinity of derivative of natural log of x over the derivative of the cube root of x. What's the derivative of the natural log of x? How about the cube root? It might be something. 1/3 of x to the negative 2/3 power is good. 1/3 of x to the negative 2/3 power. Oh, that's something very important. Limit operator. All right. So now that I know this limit is equal to the one that I originally cared about, we're going to bringing this x to the 2/3 up, so that's going to give me this. And in the meantime, I'm going to, instead of dividing by 1/3, I'm going to treat it as multiplying by 3. So let me do this first. I'll write it as 3x to the negative 1 over x to the negative 2/3. So that's going to give me, getting this limit operator. So that's going to give me 3 over x to the 1/3, right? All right. Can we talk about the limit from here? Do we need another derivative? What can we do? Question? Your words and probably not your meanings necessarily. You said it's going to get infinitely small, but it's not because it's going to have a limit. It's going to get smaller and smaller and smaller, but it's going to be bounded below by some number. And we can see that that number is going to be 0. So I have a constant numerator and a denominator that's growing without a limit, without an upper limit. Thomas, question? Yeah. So if I just break apart this, x to the negative 1 over x to the negative 2/3 is equal to x to the 1 minus negative 2/3. That's just exponent rules, which comes out to be x to the negative 1/3. And then I placed it in the denominator. Cool. Good question, though. And just to let you know, the reason I did that extra step was not for your benefit, it was for mine. I was having a hard time keeping track of all that stuff. A lot going on. Any questions about this one? All right. Tangent of x minus x over x cubed. Is L'Hopital's rule useful here? Is it even allowed? How do we know it's allowed? Yep, we got, so we got the 0 over 0 form, so I can definitely use L'Hopital's rule. What's the derivative of tangent x? Secant squared. Minus 1 over 3x squared. All right. What now? Can I look at this? Can I get this limit now? Is this an indeterminate form? I don't know. Let's think about it. What is the secant of 0? That's equal to 1 over the cosine of 0, right? 1. So I think we do have an indeterminate form again. So yes, we could use L'Hopital's rule again. I don't think that's the only way to go after this. One thing I might suggest is, all of us, myself included, I think we're a lot more comfortable with looking at cosines as opposed to secants. So I might try to re-express this. So if I find a common denominator and try to get rid of all these complex fractions, I'm going to get 1 minus cosine squared of x over 3x squared cosine squared of x. Any question about how I got there so far? Yeah, that's it. I didn't mean to. Okay. So multiplying both sides by, or numerator and denominator by cosine squared of x. Is there anywhere else I can go from here? There's a nice substitution I can do for 1 minus cosine squared. That's equal to sine squared of x. Now that I'm going through this, I wonder if it would have not just been easier to do with So tangent squared of x over 3x squared. Is that an indeterminate form? Still 0 over 0, right? Let's try this thing again. What is the derivative of tangent squared? It's not as simple as secant squared or secant to the fourth or something. You got to use chain rule. So I believe it would be, so if you think about this as y equals tangent squared of x, that outer function is a squaring function, right? So I think the first pass of the chain rule from the outer function is going to be 2 tangent x. And then the derivative of tangent is going to be secant squared of x. It's getting a little out of control, isn't it? Are we getting closer though? What tells us we're getting closer? The powers of the denominator are getting a little easier to deal with. One thing we can use is that, if we think about our Pythagorean identities, we know that sine squared of x plus cosine squared of x equals 1. Let's try to translate this thing so I can think about it in terms of secants and tangents. So I'm going to divide both sides by cosine squared of x. It'll give me tangent squared of x plus 1 equals secant squared of x. So I'm going to use that in this case just so I can avoid product rule. Still got to do chain rule, but I'm going to avoid product. So the limit as x approaches 0 of 2 tangent x times tangent squared of x plus 1 all over 6x. And while I'm writing down this next step, please stop me if you need help on any part of this. I mean, obviously, I'm about to fill up a whole slide. So if you have any questions about where we ended up, let me know. Why don't I do this? In 30 seconds? I am upstairs for 2 hours, starting at 2 o'clock today, though. I will say trig is one of those things, though, that there's a reason that you're first showed trig in pre-calculus, then calculus, then it's one of those things. It's worthless to spend like 12 weeks on it in a row, just because it's not that kind of a beast. There's a reason you look at it for a couple weeks at a time, many times. Takes a while to chip away at it and get the hang of it. All right, so are we still in an indeterminate form? Hopefully you can see that we are. We already said that tangent of 0 is 0. So I'm going to take a derivative one more time. So that'll be 3 tangent squared of x times secant squared of x plus secant squared of x all over 3. Can we do anything with this now? Is this limit defined where x equals 0? What is it? I think it's actually 1/3. So yeah, tangent of 0 is 0, but secant of 0 is 1. So kind of long way to go. That was the most we could have gone, but we got there. Any questions on that? All right. Or trig, how about this one? What should I do first? It's not indeterminate, why not? If I equals 0, true.
And that's over 1 minus cosine.
Okay.
1 minus 1.
So can I use L'Hopital's rule here? So not only is it not useful, it would be quite harmful. I'll show you why that's true in a second, but for now, let's just say this. The limit's equal to 0. I mean, that one you can directly substitute in pi, everything's well defined. But if I did do this, the limit as x approaches pi from the left, and do cosine of x over sine of x, that would lead you to believe that you're going to get -1 over 0. That would look like it's going to be infinite, right? So just a caution here. If you're going to use L'Hopital's rule, make sure that you're in one of those forms where it's valid to use it. Because here, if you use it, you're going to get misinformation. Make sense? So it is really important to make sure that you're using L'Hopital's rule for the thing that it's designed for. All right, I will tell you right now, I can use L'Hopital's rule on this, even though it seems like it looks nothing like things we've been using it for. L'Hopital's rule really does work here. So just a reminder, for L'Hopital's rule, I'm looking for things that look like this. The limit as x approaches a of some function divided by another function. And I want that to be, that ratio, f divided by g, to be some kind of indeterminate form. Everything we've talked about now has been either 0 over 0 or infinity over infinity. So is there a way to rewrite this expression to fit this thing? That derivative will not be x over x. I have to use the product rule. It'd be two different terms. Sebastian? Natural log of x to the power. Oh. So I'll tell you, yes, that's true. If we found one, we can find the other. But this is not going to help us get to L'Hopital's rule. So what I'm really looking for is can I express this thing so I have one function divided by it? What I'm going to do, essentially, I'm going to make it look a little different. So natural log of x over this thing, 1 over x. So I'll leave that there for a bit so you can convince yourself that that is actually okay to do. Is that a legal rewrite that I've made of the function I started with? No, that's not the derivative. So basically what I'm doing is this. I know that x natural log of x, that's x to the first power, right? I can treat this as natural log of x over x to the -1. So we're so used to taking the negative exponents and then re-expressing it to get rid of them. You can absolutely go the opposite direction. And then finally, I just re-expressed x to the -1 as 1 over x. Now, is this an indeterminate form? What's the natural log of x do as x gets really, really close to 0? Does not get super small, or what do you mean by super small, I guess? Does not get closer to 0. It actually gets closer to negative infinity. So let's try to unpack that a little bit. So if I'm saying, let's say y is equal to the natural log of x. If we want to rewrite that, we can say e to the y equals x, right? And I know that x is going to be getting closer and closer to 0. It's going to be positive the whole time, but it's going to be getting closer and closer and closer to 0. Think about what the power on e has to look like to get these really small numbers. Basically, you're going to have to be looking at a negative exponent. You're going to have to be looking at these fractions with really large denominators. So the numerator goes to negative infinity. What does the denominator go to? Goes to infinity. So this is an indeterminate form. I don't care about the signs on infinity, just that they both go to either positive or negative infinity. So knowing that, then I can use L'Hopital's rule. Derivative of natural log of x is 1 over x. What's the derivative of 1 over x? Yep, I'll just put it down here. Power rule stuff. Negative 1 over x squared. All right. Can I rewrite this? So I should come out to the limit as x approaches 0 from the right of negative x. Is that a limit I can deal with? What's it equal to? Question? So keep in mind what the base point is. What is x getting closer and closer to? Right. But eventually, I mean, it's getting closer and closer to 0, right? So I can get as close to 0 as I want. The fact that, and really, negative x is, it's a simple one, but it's a polynomial. It's continuous everywhere. So since I'm going to 0, which is a real number, you can do direct substitution there. Question? Yeah, so I think that we are very used to doing things like this, x to the negative k equals 1 over x to the k. And usually what we do, we go from left to right here. We see a thing that's written like the thing on the left, and we rewrite it like the thing on the right, because I think naturally negative exponents are they inherently are confusing, and we try to get rid of them. But what we did in this case, we went the opposite direction. So this x to the negative k equals 1 over x to the k. I mean, this is also true. X to the k equals 1 over x to the negative k. That opposite relationship goes both ways. So I just took my x to the power of 1 and made it 1 over x to the negative 1. So x natural log of x to the 1 is equal to natural log of x times 1 over x to the negative 1. Anything else? This is another indeterminate form if you want to go back to the original function, x natural log of x. You'll also see this written as 0 times infinity. Is that something that gets arbitrarily large, or is it something that goes to 0? And in this case, it's neither one of those things. Or sorry, it goes to 0. But there are other functions that have in this indeterminate form which might behave different. Anything else? Yeah, there are several indeterminate forms. I'm going to throw more at you. But so far you've seen 3 of them, I think, right? So only if you can manipulate it to pass through this. Yeah. L'Hopital's rule is advanced. You're fine. Like this one. This is a new indeterminate form. So x is approaching pi over 2 from the left. Let's talk about tangent first. What does tangent of pi over 2 do? Oh, what is tangent of pi over 2? Not 0. So I'm gonna give a couple things here. So tangent of x equals sine over cosine, and secant of x is equal to 1 over cosine x. What's cosine of pi over 2? 0. So what's true about both of these things? Secant of x and tangent of x. They're both undefined, right? So that means I can't do any of my limit laws that we talked about very early on, because neither one of these limits individually exists. So what's happening here as x is approaching pi over 2 from the left, you have secant of x, which is going to infinity, and you have tangent of x, which is going to infinity. So this is this new indeterminate form, infinity minus infinity. Which, on its face looks like it should be 0, but it's not well defined. Sebastian? You're saying, I mean, it's indeterminate because you have infinity minus infinity, which that's not well defined. It's undefined. So you're saying, can I write secant x minus tangent x as secant x over tangent x? Are we okay with that? That's not true. But can we rewrite these things to maybe help us? Yeah, so that's not one. Oh, I see. Okay, I see what you're saying. Hopefully you're okay with these definitions of tangent and secant, because what I can do is this: the limit as x approaches pi over 2 from the left of secant of x, which is 1 over cosine x, minus tangent x, which is sine of x over cosine of x. And since they have the same denominator, I can bring them together. So yes, infinity minus infinity is one of those indeterminate forms, but it's not the one that L'Hopital's rule deals with directly. Can I deal with L'Hopital's rule here directly? Still here, no. But that L'Hopital's rule is okay with it. Yeah. So what do I have? So what indeterminate form am I looking at here? This is 0 over 0. That's fine. So yeah, like I said, I don't care how we get to 0 over 0 or some infinity over some infinity. I can now use the L'Hopital's rule by taking the derivatives of numerator and denominator. So derivative of the numerator is negative cosine x over negative sine of x All right, can I deal with this thing now? What's the code? So is the cosine of pi over 2 defined? Is sine of pi over 2 defined? What are they? Yeah. So that direct substitution is fine there. And just because I want to caution you, even though it looks like, writing infinity minus infinity and treating infinity as a number, that looks like, oh yeah, it should be 0. They're just going to cancel each other out. I don't think this will work for L'Hopital's rule, but if you look at this, the limit as x approaches infinity of x minus x to the 10th power. If you split those up, those limits are going to both be infinity, but that doesn't mean they cancel out. So just a little caution there. If you see infinity minus infinity, don't skip to the end. It might not actually be correct. Any questions there? All right. So another thing we're going to look at are indeterminate powers. So a couple things that can happen here, or 3 things that can happen here. So what if you have a limit? So we have these functions f and g, treating f as the base and g as the exponent. A few indeterminate forms that can arise. What if they're both 0? What is 0 to the power of 0? Why is it 1? Because anything raised to the power of 0 is 1. But what happens when you raise 0 to the power? You get 0, right? So that's why this is undefined. You got 2 conflicting. Alternately, you can have, well, what if f of x goes to some number and g of x goes to infinity? Then you have this thing. Which should be getting larger and larger, but on one hand, raising 1 to larger and larger powers won't change it. But raising any number to larger and larger powers should get bigger. So that's an indeterminate form. And the last one we're going to look at is this. Infinity to the power of 0. So the thing to focus on here is limits. So if the limit of f of x going to, as x goes to a, f of x is getting closer to 1. But it might not always be equal to 1. So you could have a situation where you're, until you get to that base point, even if you can reach that base point, you might have a situation where I'm raising a number that's close to 1 to bigger and bigger powers. That would not be 1. So yes, it's all about the fact that these things are dynamic and that we're looking at limits. So let's take a look at a few of these. So this thing here. So I'm going to do this first. I'm going to call this thing y. Y equals the limit as x approaches 0 from the right of 1 plus sine of 4x raised to the power of cotangent x. So right now we have a variable up in the exponent. So think about what we've done in the past to help with that situation. I'm going to take a natural log of both sides, so I get the natural log of y. equals the natural log of this limit here. Limit as x approaches 0 from the right. So doing that allows us to pull down or bring down that power. Now I'll keep the limit there. All right, are we okay with how we got here? One thing we should do, and I mean, this is an indeterminate form, but we didn't verify that. What's going to happen to the 1 plus sine of 4x as x goes to 0? It's going to become, that's going to be 1, right? But what is the exponent? Undefined and, well, I mean, so it's undefined at x equals 0. But what's the limit going to be, more specifically, as x approaches 0 from the right? So let's look at what cotangent of x is equal to. It's equal to 1 over tangent of x, or cosine of x over sine of x. If x is positive but getting closer and closer to 0, what's cosine of x going to get closer and closer to? Yeah, could just cosine. Yeah, cosine's going to get closer to 1 and sine's going to get closer and closer to 0, right? So what you really have here is this 1 to the power of infinity indeterminate form. So, Zach, I think you were the last one that asked this question. In this situation, the limit, 1 plus sine of 4x for values of x. So raising that to some other power, then rely on it. It's not gonna... All right, so we got this indeterminate form that we're not going to be able to evaluate directly. We're going to have to find this limit and then take the basically solve for y after that. But how can I handle the limit inside these square brackets here? Gordon? Well, the indeterminate form came from the, hopefully, maybe I'm misinterpreting, but the indeterminate form that we're looking at is really, that's the only one
Is that something you could have found out?
1 to the infinity? Yeah, I mean, that's where I came from. I forgot to do it. So, yeah, I mean, that was just so the indeterminate form we're trying to get to, though, is the one that helps us do L'Hopital's rule. So is there a way we can get there? So just a refresher, we're looking for this thing. Limit as x approaches a of f of x over g of x. And what I have now is cotangent of x times the natural log of 1 plus sine 4 of x. I would love to make that look like a fraction somehow. That will work. I'm gonna make it a little more compact and do this. I'm just gonna call cotangent of x 1 over tangent of x. So I'll have the natural log 1 plus not 4 sine x, sine of 4x over tangent of x. Is this an indeterminate form? So just looking at the square brackets again, are we looking at an indeterminate form again, or can we evaluate this limit? Yes to which one? Right, so which indeterminate form is this now? At 0 over 0. So yeah, if you just directly substitute in 0, which you can do for the numerator and the denominator individually, then you're going to get 0 over 0. So I can take a derivative. So natural log of, or limit as x approaches 0 from the right of, what is the derivative of the natural log of 1 plus sine 4x? Or sine cubed? So let's set up chain rule. There's quite a lot going on here. So the natural log of 1 plus sine of 4x. Oh, it's not sine to the fourth. I'm sorry. That makes sense now. Okay. But this right here, I'm going to treat this as a composite function where f of x is equal to the natural log of x and g of x is equal to 1 plus sine 4x. So f prime of x would be what? And 1 plus sine 4x would be? Here, cosine 4x. Missing something on that one. Times 4. So yeah, they really got 3 layers of chain rule, but try to handle one of them inside the other. So this is the derivative of the numerator. So that's going to come out to 1 over 1 plus sine of 4x times 4 cosine 4x all over secant squared of x. Did I make things any easier on myself? Sebastian, you have a question? Yeah, so to take the derivative of sine of 4x, hopefully we're okay with the derivative of 1 being 0, so I'm just going to ignore it. So yeah, the derivative of sine of 4x is going to be equal to this. The derivative of sine of x, letting x equal 4x. It's a weird way to say it. Let's call it 4x, say 4x there, times the derivative of 4x. So take the derivative of the outer function, which is sine of x, evaluate it at what its inner function was, which was 4x, then multiply by the derivative of 4x. Thomas? Sure. So L'Hopital's rule, so we are applying L'Hopital's rule, which is all about, I'm not actually trying to take a derivative of both sides. The only reason I care about in doing that, I'm not really differentiating the entire equation. I just have this rule that tells me the limit of this thing in this circumstance is equal to the limit of the ratio of this derivative to this other derivative. Good question though, Jordan. In this case, I'm putting it there because when I find this limit, I'm still gonna have to figure out what y is. Because what I did do at the outset. The things I know are gonna happen. Yeah, I mean, it was definitely implied. I mean, I didn't give it to you at the outset. Yeah, so and when I'm calling it y is just the name. I'm not saying that like when we eventually find a limit here, I'm not saying that y ever actually equals that. I'm not saying there's a value of x that can make y equal that because it's a limit. It may or may not actually achieve that value. Yeah, I mean, maybe I should do this. Maybe I should call it z so we don't like. It sounds like the letter y has some extra baggage associated with it. I'm not really trying to have this functional relationship here. I'm just trying to introduce a new variable so I can. Once I find this limit, it is not the limit I care about. So I have to use that limit to get the thing I actually care about. That's the only reason I'm bringing in this intermediate symbol. And I think I've got to rush a little bit. Is this limit actually defined? What is it? 4, right? Then you can just like absolutely just plug in 0 for all these x's, right? So I don't want natural log of z, I want z. So what is this limit equal to? So probably not anything you would have expected, but the limit of this strange expression is e to the 4th power. What? Maybe. I don't want to. But certainly when you bring in natural log, you're involving my good. So it may. I have a couple more examples on here that I will post online. It's just one more. I would recommend going through and practicing with this one. I'm not going to do this today, obviously, and I'm not going to do it on Monday either. We're going to start chapter 4. But I think it would be a good exercise if you want to get some independent practice on that natural log. Get that natural log involved in finding limits. I am going to post a quiz tonight, and it'll be due on Wednesday. Homework's due tonight, right? 3, 5. Okay, I'll make this one due on Tuesday night.